Hello. Today I'll be presenting my CS 691 final presentation on physics-informed neural networks with partial differential equations in Julia. I will start by sharing my screen of the presentation. So this is physics-based generative modeling using the physics-informed neural networks in Julia, as I said, and it's using this neural PDE package, a package developed and referenced by paper 74 on the syllabus and presented in another paper that I'll briefly talk about as cited on the bottom. I performed three experiments using the neural PDE package. And these three experiments are present in various papers studied in the class. Although the code I replicated is not from one specific paper, the papers with code for paper 74 on the syllabus did lead me to this package in Julia, and furthermore to the paper that presented the package, and so on. So an overview, like I said, this is a Julia package for implementing physics-informed neural networks with partial differential equations. I perform an experiment modeling the Poisson equation, a 1D wave equation, and the Burger's equation. These partial differential equations are very common throughout physics. With wave propagation, the Poisson equation is prominent really everywhere. The Burger's equation is very prominent in a lot of fluid and thermodynamics, and is seen as a sort of simplified version of the Navier-Stokes equation. So the experiment is to model the behavior of these equations with a neural network, given the equation's boundary conditions and the domains, using graphical representations of the equations. Through the use of partial differential equations, the model is enhanced and able to do this without data, which is the main problem statement, the main part of this experiment. Can we replicate this code, or can we replicate these experiments on these three equations, modeling them in Julia with no data, solely with the boundary conditions and the domains and the equations? So it's a sort of demonstration of the power of physics-informed neural networks, and the underlying theme is that this is vital in data-limited environments. So in terms of related work, paper 1 introduces the neural PDE package. Paper 2 has the implementation of this package linked to it on papers with code. Like I said on the first slide, and paper 2 is paper 74 on the syllabus. So that's sort of the paper that I started with, and which is a paper that provides an overview of neural networks, of physics-informed neural networks, rather. Paper 3 in my references is the initial paper from 2019 that introduces the PIN architecture. And then paper 4 performs some experiments with PINs, including modeling Burger's equation. That's a main source for me. 5 and 6 address the failure modes and explore issues in the loss landscape, which was something that I definitely wanted to pay attention to throughout the development of the models. Paper 7 investigates overfitting and other sort of failure modes and issues in the PIN architecture. And papers 5, 6, and 7 really vital in my discovery that, because the architecture is so new, because research is limited, that there are some major issues despite the PIN architecture's strength. 8 introduces a new PIN architecture using a modified reptile algorithm that was quite interesting, and this included some experiments. The more important and more relevant to this presentation, it includes some experiments with the Poisson and Burger's equations, and thus was a very good reference. Finally, 9 and 10 model wave propagation, including 10 seismic wave propagation, which I found to be an interesting propagation of PIN, since it's very, very much real life. It's very immediately pertinent to real life, given the danger that seismic activity can present to communities, especially in certain hot zones such as the West Coast and Eastern Asia. Papers 11 and 12 contain some of the code. So that's the references to the code. 11 is the reference to the actual GitHub of the neural PDE package, where I found a lot of the documentation. and some of the inspiration for the source code. And 12 is key in the Burger's equation experiment, particularly the analytic solving function, which I'll talk about very soon. In terms of methods, the neural network architecture, the actual neural network, is a very simple, starts with 2 dimensions, and then it heads to 2 hidden layers of 16 nodes as the display shows here, and it condenses into 1 output layer. This is true for all 3 experiments, and at first I was very committed to improving this architecture, but changing the architecture from this and adding more hidden layers or adding other features or changing the sizes of the hidden layers had very disastrous results in terms of the quality of the output. Disastrous enough that it wasn't worth including in the presentation. Worth noting that this was really what worked. And I'll get to the implementation of that later and talk about, maybe that's connected to it. The training of these models uses this quadrature training, which is present in NeuralPDE. So it basically uses an integral of the current state for a loss function in terms of you start with a boundary condition and you progress to different conditions throughout. And that's the integral of that state is a main way that the PDE is factored into the actual loss landscape. So through 6,000 iterations in the Atom Optimizer, it's trained and it's evaluated using the convergence of the model via just a simple loss plot, and then the standard error, the error between the predicted and actual output. And the actual output is calculated with this analytic solving function, which I briefly mentioned earlier. So the analytic solving function, which is a main strength of Julia in this due to its capabilities in mathematical calculations, analytically solves the equation and generates the output. So it's an analytical way to perform the generative modeling without the neural network, and it's used to verify the efficacy of the neural network through the error. So the Burger's equation uses the analytic solving function to calculate its boundary conditions, which I'll talk about in one moment. So this slide details the PDE's boundary conditions and domains for the functions. So for Burger's equation, or even for the Poisson equation and the 1D wave equation, the ranges are from 0 to 1. For Poisson equation, it's x and y. For 1D wave equation, it's x and t. So those are the domains. And the boundary conditions are here. For Poisson equation, it's all zeros. And for the 1D wave equation, there are also some zeros other than this x times 1 minus x term here for the t-intercept at 0. So those boundary conditions provide the foundation. In terms of Burger's equation, the domain goes from x to 2 pi, and the domain of t goes from 0 to a very small number, 8.796 times 10 to the negative 5th. And that second term, the t domain, is calculated using the analytic solving function along with the boundary conditions. The boundary conditions are calculated using the analytic solving function at the x and t intercepts, so where the x and t equals 0. In terms of the equations themselves, these terms are all duplicated in Julia using a mathematical package to help establish the actual differential terms, since that's a little bit more complicated to actually represent programmatically. And that's true for each of the 3 equations. They each feature a second order partial derivative. So that is another layer of added complexity that really Julia was able to expedite the simplicity, or rather of the writing of these things in the programming of these second order partial derivatives. That was key in the implementation, which I'll talk about a little bit more right now. So implemented in Julia, as I said several times, and the NeuralPDE package is used. So the deep learning package used in conjunction with NeuralPDE is called Lux. which is a common deep learning package in Julia. And so some of the issues with the implementation, obviously compatibility, having the correct packages and versions installed was always going to be the main issue. And it required some, a great deal of research and nitpicking to make sure that I downloaded and reverted certain versions back to other versions and upgraded and updated certain packages. And some other issues were displaying the loss. There was it was a little bit hard to find how to derive loss from the actual neural network object that we that I coded. Also, Julia is a bit of an unfamiliar programming language to me, but its strength in terms of mathematics made it so efficient. This code ran very quickly without near as much complexity as if I were to do this in Python. The analytic solving functions were a final issue, especially for Burger's equation. So finding the correct analytic solving function for Burger's equation was difficult, and I derived it from paper 12 or source 12, which is a GitHub repository. And this was really vital in the Burger's equation experiment actually functioning as desired. In terms of the results, so the first results I'll go over, the Poisson equation. For the Poisson equation, the predicted output and the analytic output obviously look very similar. There's some distortion of the predicted output if you look closely, especially in the corners here. It looks very evident. In terms of the major peaks in error, there are really only three, both as x and y approach 1 in slightly different spots, but both around the middle of the other variables range, just sort of on the boundaries, on the edge of the actual graph. But overall, it's very clear to see this output is what is desired. It's the elliptic output. And so the error is fairly minimum, even at peaks. If I go back, this error, the brightest yellow, the highest degree of error, is only just above 0.006, where the range is from 0 to 0.05. It's a small error. The model converges as the loss plot shows here, and there are really no increases in loss after the initial convergence, which raised for me concerns of overfitting or possible issues. But realistically, I found that this was the best amount of time. Training for the 6,000 iterations was really no problem. Now for the 1D wave equation, this shape also slightly elliptic, although split and shifted a little bit, is the correct shape. A main noticeable error is in the analytic output. This central line remains straight as it goes towards the top of the t-axis here, but this line actually curves in the predicted output. That's the main difference, but it's clear to see that the output has been correctly modeled, and the error here is very minimal. Even that the actual graph goes up to 0.25 and the error peaks at 0.01. Peaks at just above 4%. The error, so it's a very minor error here in the 1D wave equation. These are probably the best results. The semi-elliptic output, the shifted elliptic output, if you will, as desired, is shown. In terms of the error, there are more peaks, but they're very minimized. So compared to the Poisson equation, there are certainly more spots where error comes up, but they're smaller and they're definitely have a lower magnitude. In terms of the loss convergence, there are several small peaks here between about 1,500 and 4,000 iterations. They're very small peaks, but of course, any increase in the loss is notable. But it does converge by 6,000 iterations, showing that, again, the two methods of evaluation, the error and the loss, this model does generate the correct output. Finally, the Burger's equation produces probably the most interesting output. There's some clear issues you can see in the predicted and analytical output. The bars are the biggest one throughout is that the bars in the predicted output are very condensed and the central area is larger. Also, this first yellow bar obviously doesn't appear right. The error is a bit harder to read, but clearly there's a significantly higher degree of error, closing in on about 30%, or perhaps above 30%, given that the range of this is to about 2 pi, or just above 6, and the error goes up to about 2.25. So there's some clear error, and there's some clear performance issues, but the fact of the matter is this is clearly the desired output in terms of generation. To an extent, the shape is right. It's not something completely off. The error is of course it's minimized, but it could be better. And certainly this was the best that I was able to get the code to achieve. The model does converge, but the loss plot is far more interesting. It peaks about 12 times between the first and around 4,000th, slightly after 4,000th iteration. So the loss plot does eventually level out, but the training is far more difficult for the Burger's equation modeling, showing a bit of a difference from the previous ones. So in terms of discussion, the main takeaway and the main thing that I learned is the power of these physics-informed neural networks in data-limited circumstances, especially in modeling physical processes. Something else I learned was how to really factor in and really hone in on the importance of boundary conditions and domains. Completely the difference between the model working and generating correct output and the model generating wildly incorrect output. In terms of model evaluation, the error and loss were really the standard. And in terms of using the neural PDE package in Julia, these were the two that made the most sense. Since the output is graphical, if the shape doesn't look right, then the output is wrong, and that was a big that really aided my debugging and my actual development of the models. And then of course factoring in the loss is always very important. Some future applications of this, I'm very interested in using partial differential equations to enhance deep learning in the field of finance, and I found some literature and code related to this, but unfortunately I was just unable to get it to work. I hope to. I plan on diving much deeper into this as early as next week and over the summer. I'm very interested in financial and option trading research, and that's what it applies to. Is the option trading carries a fair amount of differential equations. Nonetheless, the physics-informed neural network and the partial differential equation will definitely be present in my future deep learning, especially generative modeling, when partial differential equations or ordinary differential equations are available. So the main conclusion is I found that Julia was very integral in the functioning of this code due to its efficiency and its simplification of these complicated mathematical terms. And most importantly, the physics-informed neural networks can perform generative modeling without data, something that cannot be said about many applications of generative modeling, deep learning, and machine learning as a whole. So it's a very unique application, in my opinion. These are the references. They'll be the same on the paper. The 12 references, and as I mentioned, these bottom two are GitHub repositories with some of the code that was really vital in the production of these results. So thank you very much. Please feel free to reach out via email with any questions. I really enjoyed this class and this experiment, and this was a really great experience. I'm really happy to have learned about generative modeling, generative deep learning, and I'm thankful for my time in class. So thank you very much. Please enjoy your summer, and again, feel free to reach out with any further questions about the paper or anything else related to the project. Thank you.